Alright, hello everybody. Since I missed class yesterday on Tuesday, I'm not feeling very well. I'm still not feeling very well, but I'm getting closer to 100%. So I thought I would make a video for the first part of section 17.6 about surface integrals. Now, everybody hopefully recalls that we so far have studied curves, and we know how to parameterize curves as vector-valued functions of a single independent variable t. And we've got some parallel concepts. If you look in the box here, so I'm just looking at the textbook. If you look at this little box right here, when we talk about curves, we can do things like find arc length. We can use line integrals to find the area of a curtain, or we can use line integrals to find, we can calculate line integrals of a vector field over a curve to do things like work, circulation, flux. And of course, parameterizing a curve, there we can always find a one parameter description in terms of t. Okay. Now the parallel or corresponding concepts with regard to surfaces are, just like you can find the arc length of a curve, we're going to develop a way to find the surface area of a surface coming from a function of two variables, z equals f of x, y. Now with curves you can find line integrals through vector fields to find things like circulation, work, flux. We're going to also do surface integrals to essentially surface integrals are going to allow us to do things like essentially find surface area. We can also throughout a surface living in a vector field, we can find the outward flux of the vector field along the surface. And before you do that, before you actually calculate surface area or surface integrals, we're going to need to find a two-parameter description of the surface itself. So this is like parameterizing a surface instead of parameterizing a curve. So here's the basic idea. Let me change the size a little bit. So again, if you read the top, a curve defined in R2 is defined parametrically as by a function r of t with component functions x of t and y of t. It only requires one parameter and two dependent variables, x and y. And if we step up one dimension and we want to define a surface in R3, we're going to need two parameters and three dependent variables. So instead of using t as my parameter, this time my vector valued function that describes the surface will be a function r of u and v, and then you'll have three component functions. The dependent variables are x, y, and z, and each of those components depends on u and v. Now, we can make an assumption that the parameters vary over a rectangle. Okay, so a rectangle R, which is going to be the set of all points u and v, where u ranges from a to b and v ranges from c to d. And as the parameters u and v vary over R, the vector r of u v is going to sweep out a surface. So you can play with this in the textbook. Here's the little rectangle that describes u and v, or sorry, u and v are going to describe a rectangle. And as you vary throughout the rectangle, that if you look on the right, there's a vector directed from the origin whose tail of the vector is going to point to a point on the surface. So every point u and v corresponds to a vector giving you a point on the surface. Okay, that lives in 3 space. So now here's the handout, and I will be posting this handout onto Canvas along with the video. So if you're watching the video, you can find the worksheet if you like. And here's going to be the command for a surface plot. You're going to use parametric plot 3D, and then you have your x function, y function, and z function. So you're going to parameterize x, y, and z in terms of u and v. You're going to enter your three component functions, and then you're going to give the range of values for u and v on the back end there in the second and third set of brackets. So I'll start out simple. I want to find a parametric description of the plane x minus 2y plus z equals 4. So I'll first find the parametric description, and then I will show you how to use parametric plot 3D. Okay. So for planes, it's very, I think, pretty basic, very simple. What you're going to do, and hold on, forgive me for just a second, I have to fix my window here. Okay, so find a parametric description of the plane. Now with the plane, it's pretty simple. You can just let the u parameter, sorry, that's a mu, I'm still used to stats, writing u's. So u, you can let that be x, you can let v be y, and then if you solve for z, you're going to get, well, first 4 minus x plus 2y, and then substituting u and v in, you're going to get 4 minus u plus 2v. And that looks ugly. Let me rewrite that. Maybe I'll write it below this time. You're going to get 4 minus u plus 2v. Okay. Now when you do the Mathematica code, I'll do this at the bottom. The x function was going to be u, the y function is v, and then remember we solved for z and got 4 minus u plus 2v. And you can range these from whatever you want. I'll just do minus 10 to 10. So I can make my viewing window as large or as small as I want. And I'll hit Shift Return on my Mac, and there would be Mathematica plotting my plane. Okay, so for planes it's very simple. Just let x be u, let y be v, and then when you solve for z you just need to replace x and y with u and v respectively, and then you can choose any viewing window you want. Okay, so now what if I want to find a parametric description of a cylinder of radius 3, and then this cylinder is going to extend along the y-axis from y equals 0 to y equals 5. So y is kind of going to be a free variable here, and let's see how we do this. Okay, so what you can do first is you can notice, sorry, not y, but what you can do is you can write an equation for the circle in the xz plane of radius 3, so x squared plus z squared equals 9. And if you thought about parameterizing this with respect to t or with respect to theta, x would equal 3 cosine theta, and z would equal 3 sine theta, and y, you can think of y as being a free variable where it roams from 0 to 5. Now, for parametrizing this or finding a parametric description, now in this case what I would do is let u equal theta, and you can let v equal y, and then what you know now then is since u is theta, that's going to range from 0 to 2 pi, and since v is y, y is going to range from 0 to 5. So what you get then is the x function is going to be 3 cosine u, z, or let's do x, y, z. Y is going to equal v, and z is going to equal 3 sine u. Okay, and then if you need to go back to see this, you can, but I have to close down the image here to type in the Mathematica code to plot this thing. So you can start typing your parametric plot 3D. Our x function was 3 cosine u. Remember, y was v, and z was 3 sine u. U is going to range from 0 to so u goes from 0 to 2 pi, v is going to go from 0 to 5, and I hit shift return, and then what I get is I get a cylinder of radius 3 that extends along the y-axis from y equals 0 to y equals 5, as desired. Okay. Now the next thing I'm going to do is I'm going to do a half cone. Now generally what you do is planes are pretty easy. Notice that the cylinder, I essentially just used polar coordinates for the most part. And you know, the same would be true for a sphere. If I was going to plot a sphere, you would probably use spherical coordinates, so you'd write x, y, and z in terms of spherical coordinates, and you would let, say, theta be u, you would let phi be v, and then you'd have some fixed radius of the sphere, and you could do a parametric description of that. So now what if I want to find the parametric description of a half cone, a vertex at the origin, and I want height 5, and I want a radius of 3 on the top? Now, to find a parametric description of a half cone with the vertex at the origin, height 5 along the z-axis, and radius 3 on top. So you can think of a picture of this. X. You can think about the x-axis, y-axis, and the z-axis. And if I think about my cone, it's going to look something like this. The top is going to be a circle of radius 3. So if I want, I can think of it this way. You can think of the height of the cone being a. So I'm going to do this in general first, and then hard to see in my picture, but there would be my radius r. And the way you could describe this cone would be in cylindrical coordinates, r theta z. Now r is the radius, and Now I made a slight mistake. Let's actually think of the radius as A. I'm just going to stay consistent with the textbook, and I'd rather think of the height of the cone as H. And then that way, now R would range from 0 to A. Okay, so what this means is that we're just thinking of plotting the surface or the edge of the cone, and at the bottom of the cone, at the origin the radius would be 0, and at the top of the cone the radius would be A. So as you move throughout along the edge of the cone, the radius goes from 0 to A. Okay, so this one we're pretty confident with. Theta is always going to go from 0 to 2 pi. The question is, what is Z? Okay. Now you can use a little bit of triangle trig. If I look at the slice of if I just look at the projection of the cone onto the ZY plane, this would be the height H, and this would be the radius A. And I want to find the Z coordinate. Okay, so this triangle that I drew, that's the projection of the entire cone. And then, I guess, if you pick an arbitrary point, right, you're gonna look at a smaller triangle inside of that triangle. So let me draw a picture of that smaller triangle. That has arbitrary radius R and height Z. Okay. And this would just be thinking of an arbitrary point on the cone right here. Okay, that point has coordinates x, y, z, and I can think about the height of the smaller triangle as the z coordinate, and then the radius, think about slicing the cone anywhere, you're going to get a circle of radius r. And if you use similar triangles, what it says by similar triangles is that z over r, so the ratio of those sides has to be the same as the ratio of the sides of the larger triangle, which would be h over a. And that tells me that z is going to equal rh over a. So that's what's going to go right here. So that would be the cylindrical coordinate description of the cone. Okay. So that the z coordinate is always rh over a. Now, I need to find a parametric description for this, r view v. And what I'm going to do is I'm going to let actually, I guess first what I'm going to do is I'm going to look at r equals, or x equals, so use polar coordinates. X is r cosine theta, y is r sine theta, and I guess z is just z. But now we know that z is rh over a. Okay. Remember, a is the radius at the top, and h is the height of the cone. Now, r cosine theta. If you take this equation for z right here, z is rh over a, and you solve that for r, you get az over h cosine theta. Y is going to be az over h sine theta, and z is just going to stay rh over a. Okay, so now if I rewrite that again, x is now az over h cosine theta. Y is az over h sine theta. And I'm actually just going to let z be a free variable. Z is free to be whatever you want it to be. And that's just going to represent the height. So z just represents the height of the cone at any point on its edge. And what we're going to do here is I'm going to let u equal theta and let v equal z. And now h is going to be the height of the cone, which is 5. A is going to be the radius of the cone at the top, which is 3. And my parametric description then, r of uv, is going to equal, the first component is going to be 3/5 v cosine u. The second component would be 3/5 v sine u, and the third component is just allowed to be free. That's just going to be my z or my v coordinate, and v goes from 0 to 5, and theta goes from 0 to 2 pi. Okay, so I'll go ahead and plot that with Mathematica. Okay, so the first coordinate, remember, was 3/5 v cos u. The second component was 3/5 v sine u, and the third component, z, was just v. Theta, which is now u, goes from 0 to 2 pi. And the v component just goes, well, the cone ranges from a height of 0 to a height of 5. I plot this, and I should get a beautiful cone, radius 3 at the top, and height 5, which I think you can see looking at the plot. Okay. So again, the key here was thinking about polar coordinates, or cylindrical coordinates, to plot the cone. Okay, so let's go ahead and do a parametric description of a sphere, the surface of a sphere of radius 3 centered at the origin. Now, to do this, remember we can, when we were doing double and triple integrals, things that have a spherical shape, we could find volumes of the sphere by using spherical coordinates. And I think, if you recall, the equation of a sphere in spherical coordinates is just rho equals 3. That's the equation of the sphere centered at the origin. And then remember, you have an x coordinate, which would be rho sine phi cos theta. Y would be rho sine phi sine theta, and the z coordinate was rho cosine phi. Okay, now the easy thing to do here is to let u equal your theta, let v equal your phi, which remember goes from 0 to pi over 2, and then that way, when you write this down now, r of u comma v as a vector valued function, x would be rho sine phi cos theta, which rho is 3, and you'd get a sine v cos u. Y would be 3 sine v sine u, and the z coordinate would be 3 cosine v, and theta goes from 0 to 2 pi, and sorry, not theta, remember theta is now u, so u goes from 0 to 2 pi, and v, which is phi, goes from 0 to pi over 2. Okay, so now I got to get rid of the writing to plot this with Mathematica. Again, we'll do parametric plot 3D. And x was 3 sine phi cosine theta, which becomes 3 sine v cosine u. Y would be 3 sine v cos u. And z would just be 3 cos v. And then I need to specify that u goes from 0 to 2 pi, and v goes from 0 to pi over 2, and I should plot this. Now I'm supposed to be getting a sphere. This probably means I had a mistake and I see it in my y component, which should have been sine. There we go. And my other mistake was actually that v should be going from 0 to pi. So sorry, that was my mistake. Remember, in spherical coordinates, phi ranges from 0 to pi. And remember, I just let phi be v. So I should have done my range of phi or v values from 0 to pi. And then there we go, I get the surface of a sphere of radius 3. Okay, so the the next step is, okay, so now if I wanted to do surface integral, to do surface area, or we're gonna do surface integrals to compute outward flux of the surface living in a vector field. So now just imagine that you've parametrized your surface with a function r of u and v. Now remember, u and v, the range of u and the range of v are going to essentially give you a rectangle in the uv plane, and just like with any other integral, what you can think of that as your domain, and you can chunk it up and break it up into smaller rectangles. So if you look at the interactive figure in the textbook, you have a first rectangle in the bottom left corner. Let's say that that's R1. The width would be delta U, and the height would be delta V. And that rectangle R1 gets mapped onto the surface on the right. You can see that little shaded patch S1. Okay. Now, the idea is that you would probably want to basically, and also there, at first we're going to imagine that there's also a function of, we're going to be doing a surface integral of a function, of a 3-variable function. That function eventually goes away because we let the function equal 1 to find the surface area. Okay. Sorry, I got a call there from a solicitor. Okay, so now, if you, at the bottom left corner in that rectangle in the domain, you can let UKVK be the lower left corner of a point in the kth rectangle. Technically, you could do this with any point if you want. Now, UKVK corresponds to a point P with coordinates x of UKVK, y of UKVK, and z of UKVK. So that corresponds to a point on the surface. And that would be on the kth patch, S sub k. And to construct the surface integral, you're going to define a Riemann sum. So what you're going to do is you would add up the function values. So you have an f, you have a function of 3 variables, and you would multiply that by the area of each of the respective patches. So in the case where f equals 1, you would be adding up the area of all of those k patches to approximate the area of the surface. Okay. Now, the idea is I'm going to kind of use little tiny tangent vectors or parallelograms to approximate the area of the kth patch. So what you can do is, we're going to do this in just a second, so T sub u is going to be a vector tangent to the surface in the u direction. t sub v is going to be a vector tangent to the surface in the v direction. And then we're going to scale those with delta u and delta v. So tu delta u would be the that rectangle that's sitting above that patch. Tu delta u would be, I guess, the width, and tv delta v would be the I guess height, width, length, width, whatever you want to think of it. And then if you look there, there's a vector that's normal to that little tangent plane. And now I could find the area of that tangent plane patch sitting above the patch on the surface, and it would be the magnitude of tu delta u crossed with tv delta v. Delta u and delta v are scalars, so they come out. And that would approximately be the area of the kth patch. So you take the cross product of the tangent vector with respect to u, crossed with the tangent vector with respect to v, multiply it by delta u and delta v, and that would be, and where I'm looking right here is I'm looking at this little thing right here. So that's an approximation for the area of the kth patch. Now, because the surface is parametrized by r in terms of u and v, a tangent vector corresponding to a change in u with v fixed, so t sub u, is just partial r over partial u. So each component is partial x, partial u, partial y, partial u, and partial z, partial u. So you're just taking the derivative of your component functions of r with respect to u. And you can do the same thing with a change in v with u fixed, so t sub v, and that would just be partial x, partial v, partial y, partial v, and partial z, partial v. This would be really similar to like finding your gradient field, if you want to think of it that way, or like finding a gradient. And then what I'm really concerned is, I'm going to scroll down to the bottom. So your Riemann sum, your Riemann sum, the delta sk, would get replaced with magnitude of tu cross tv, delta u, delta v, and then letting the number of rectangles go to infinity, or essentially letting your change in u and change in v go to 0. This is going to make your rectangle smaller and smaller. That's going to lead to a definition of the double integral over a surface of a function of 3 variables with respect to surface area. It's the limit as delta u and delta v approach 0 of your Riemann sum, and that becomes a double integral over the region R. So that's the rectangular region given by u and v. And then what you would do in the function f is you would substitute in your parametric descriptions of x, y, and z, and then you would do the magnitude of tu cross tv, and then integrate with respect to a. Okay, and there's going to be times where you're going to probably want to use, now this would be a double integral over the region R in rectangular coordinates. There might be times where you want to use polar, cylindrical, something like that, but there is our definition. So f is a continuous scalar valued function on a smooth surface S. So it's just a function defined on the surface, and the surface has a parametric description. U and v vary over a rectangle, and then you have tangent vectors tu and tv. They're supposed to be continuous, and then tu cross tv is a vector that's normal to the surface. And then the surface integral of f over s, well, it was given above. And if f of x, y, z equals 1, the integral equals the surface area of S. Okay, so let's go back to the handout. We'll actually do this. We'll compute we'll find some surface area. Now, I'm not going to lie to you. Doing the magnitude of tu cross tv can sometimes be tedious. So, for example, if I want to find the surface area of a sphere of radius a, what you would probably do is first parameterize the sphere of radius a, and you would use you'd have to parameterize the sphere of radius A first, and the radius is A, so r of uv would be A sine v cosine u. And then the next component, sorry, that's a sloppy cosine u. The next component would be A sine v sine u, and the third component would be A cosine v. Okay, so that would be your parametric description of the surface, the sphere of radius A. And then the next thing you'd have to do is find Tu and Tv. Now, I was lazy, I guess. I just did this up here. If you look up here, eventually I'm going to do cross product, and I just let Mathematica do this. This is Tu, and this is Tv. And I actually might have this backwards. I might have this in the other direction. I think I do have this in the other direction. And it doesn't matter because you're going to take the magnitude of this anyways, so it doesn't matter if you do Tu cross Tv or Tv cross Tu, because they're just negatives of each other. So that's actually Tv and that's Tu. And then this is the messy, ugly cross product. The first component is A squared cos V sine U squared. The second component is A squared sine U squared sine V. And the third component is also just an ugly mess. So I'm probably just going to use Mathematica to do this. First I'll write down the integral though. So now if I want the surface area, it's supposed to be, the formula is, it's the double integral over the surface, and it would just be Tu cross, because remember f would be equal to positive 1 in this case. It would be Tu crossed Tv ds. And after doing a parameterization, oh, sorry, there's no ds in that part. Or there's no Tu cross v. It would just be ds. This is the double integral over the rectangular region R. And then it would be magnitude Tu cross Tv with a dA with respect to area. Okay. Now, this right here that I've underlined, this is Tv crossed with Tu. So not only do you find the cross product, but you'd actually have to find the magnitude of that. But I'll go ahead and write it down. So when I do this, the double integral over the region R, dA is going to become du dv. So you do your u limits first, 0 to 2 pi, and then to get the entire sphere v, remember, was phi, you'd have to go from 0 to pi. And then you'd have to take the magnitude of Tu crossed with Tv. This is not as bad as it looks. So now what you would do is you would take, if you look up there, I've underlined Tu cross Tv. So I would take A squared cosine V sine U, well, sine squared U. By the way, sorry, in this problem I have u and v backwards. It doesn't really matter what angle you let be u and which angle you let be v. But if I'm going to do du dv, I think I have it backwards here. I actually think if I'm going to do du first, in this case I let u be v. Sorry, in this case I let theta be v. So if I do du dv, it'd be 0 to pi and 0 to 2 pi. So it'd be a squared cosine v sine squared u plus the next component would be a squared sine squared u sine v squared plus, and then the last one, if you look at the third component, you can actually factor out an a squared cos u cos v, and then an a squared cos u sine u, and the cos v squared plus sine v squared becomes 1. So this would just be an a squared cos u cos v squared. Oops, I don't want that going on the whole thing. Erase. And then this is supposed to be du dv. Okay. Now, I need some more room, so let me erase this up here. Now I have to simplify that integrand. And it looks like it's going to be pretty messy. I'll let you verify this on your own in the book. It's exercise 70 if you want to do this. But as messy as that radical looks, I'd claim it really just becomes a squared sine u du dv. And I'll let you verify this on your own, but this becomes 4 pi a squared. Okay. So I don't think that's very hard to integrate. The antiderivative of sine u is minus cosine u. You plug in pi, subtract what you get when you plug in 0, and I think that just gives you a 2a squared. And then doing the outer integral with respect to v, since 2a squared is a constant, you just multiply by 2 pi and you get 4 pi a squared. So that is the surface area of a sphere of radius a. And yes, this one would be very tedious to do by hand, so I cheated. I used Mathematica to do the cross product of tu and tv. I did plug that all into the magnitude of tu cross tv to get that big square root in the integrand. But that does simplify pretty nicely. That whole thing under the radical becomes a to the 4th sine squared u. You get some. It looks pretty messy. It looks pretty awful at first, but it does end up becoming pretty nice. Okay, so the last thing I can do is I can go ahead and I can find the average temperature on the boundary of a sphere. So if I have a temperature function, T of phi theta, this is 10 plus 50 sine phi. Now, so basically this temperature function is already in your spherical coordinates. And in the textbook, what they do is they actually let u be phi and v equal theta. And it doesn't really matter. either way. You just have to recognize that u is really ranging from 0 to pi and v is ranging from 0 to 2 pi, but you can do it either way. Now if you want to find the average temperature, you would just have to integrate the temperature function and divide by the surface area of the sphere. So we already did this in the previous problem. The surface area of the sphere is 4 pi a squared. And also remember in the previous problem, this was kind of messy. You can use this if you want to. If you find Tu cross Tv, and you find its magnitude for a sphere of radius a, this is always a squared sine u. Or if you had u and v switched, it would be a squared sine v. Okay. So what I'm going to do is, if I want the average temperature, I'm going to first just integrate the temperature function. So I'd be doing the double integral over s, and I can integrate the temperature function. Now it'd be 10 plus 50 sine phi, but I let phi be u, and you'd integrate this with respect to surface area. This becomes a double integral over the rectangular region R of 10 plus 50 sine u times Tu cross Tv dA. This equals, now if I integrate this, it's the integral from 0 to pi. That'd be your first integral, and the integral is 0 to 2 pi. So this would be doing dv du this time, and it would be 10 plus 50 sine u. Tu cross Tv we saw was a squared sine u, and I'll be doing dv du. And you can go ahead and do the integrals. The inner integral would be easy because with respect to v you just pick up a 2 pi a squared, and by the time you're done, just to save time, I'll let people, if you're interested to do this by hand, you can. Oops. This integral would equal 10 pi a squared, and then in parentheses you get a 4 plus 5 pi. Okay, so that's that's the integral of the temperature function over the sphere. And then if you want the average temperature, you would just take that integrated temperature and divide by the surface area, which we got from the previous problem. So the average temperature is equal to this 10 pi a squared times 4 plus 5 pi. So that was the integral of the temperature function over the sphere. And then you would just divide that by the surface area, 4 pi a squared. The a squareds go away, the pi's go away, and then this would equal, when you distribute the 10/4 to the 4 plus 5 pi, you would get 10 plus 5/4 pi, and that's approximately 49.3 degrees. Okay. So that would be the average temperature over the boundary of the sphere. So what we're going to do in class on Thursday is we're going to do surface integrals on explicitly defined surfaces. So rather than implicit, we just did implicit surfaces today. It becomes a lot easier to do surface integrals over explicitly defined surfaces. That way you won't have to do a parametrization. So the only time you have to do a parametrization is if you have an explicitly defined surface where you can, like our cylinder, if you're integrating over a cylinder, a cone, a sphere, where you can either use cylindrical, polar, or spherical coordinates. then you have to find a parametrization. But if I have a surface given explicitly as like z equals a function of x and y, there's a much easier way to do that, and we'll do that in class tomorrow. Hopefully everybody gets a chance to watch the video, and I'll see you tomorrow on Thursday. Thank you.